Hello my friends, and welcome back to Sky Creative Channel. Watch as massive cranes lift hundreds of tons, cutting-edge composite materials reshape the future, and engineering teams accomplish in days what once took years. Let's get started. You know, there's something deeply satisfying about watching a bridge come together, isn't there? Reminds me of the great American bridge building era when we connected this vast nation of ours. Today, we're looking at the Pelješac Bridge in Croatia, and let me tell you, this is engineering on a scale that would make those old-time bridge builders tip their hats in respect. Built by the China Road and Bridge Corporation, or CRBC as the engineers call it, this isn't just any bridge. Standing at 2.4 kilometers long, it's the longest bridge in the Adriatic region, and it solved a problem that had troubled Croatia for decades. See, the southern part of Croatia was cut off by a small strip of Bosnia and Herzegovina's coastline. This bridge finally reconnected the country without requiring border crossings. Sometimes, the best engineering solutions are about bringing people together. Now, let's talk about how they actually built this magnificent structure. The construction method they used is called the balanced cantilever technique, and it's a marvel of modern engineering that has its roots going back to the 1950s in Germany. Think of it like building out from both sides of a tower simultaneously, keeping everything perfectly balanced as you go. It's the same principle you might remember from those old erector sets, but scaled up to handle thousands of tons. The foundation work alone tells an incredible story. They drove 579 steel piles deep into the seabed, some reaching depths of 115 meters. That's like stacking the Statue of Liberty twice underground. These piles had to punch through layers of soft sediment to reach solid bedrock. The pile driving equipment they used was specialized hydraulic hammers mounted on floating platforms, capable of delivering precise, powerful blows that could be heard echoing across the water. Each pile was carefully monitored with modern sensors to ensure it reached the required bearing capacity. The bridge stands on 6 massive piers rising from the Adriatic Sea, and creating these required some serious heavy lifting equipment. They employed what's called a climbing formwork system. Picture this, enormous steel forms that grip the growing concrete column and literally climb up as each section cures. It's like a mechanical caterpillar working its way skyward. Each pier required multiple concrete pours, with the mixture being delivered by specialized concrete pumps that could push the material up to heights exceeding 80 meters. Here's where it gets really interesting for us machinery enthusiasts. The main construction workhorse was a pair of massive movable scaffolding systems, or MSS units as they're called in the trade. These behemoths weighed about 580 tons each and could span 85 meters. They position themselves on a completed section of bridge, then serve as a platform for workers to build the next segment. Once that section was done, these giants would roll forward on rails built into the bridge deck itself, ready to repeat the process. It's like the bridge was building itself forward, one segment at a time. The concrete segments themselves were engineering marvels. Each box girder section was cast using sophisticated steel formwork with hydraulic controls that ensured millimeter-perfect accuracy. The concrete mix was specially designed with marine-grade additives to resist the corrosive salt environment of the Adriatic. They used high-performance concrete with compressive strengths exceeding 50 megapascals, ensuring this bridge would stand for generations. Now here's a detail that would have amazed the old bridge builders. They used computer-controlled tensioning systems for the post-tensioning cables. These high-strength steel cables run through the concrete and are pulled tight with precisely calibrated hydraulic jacks, creating internal compression that helps the bridge carry enormous loads. The tensioning process had to be done in a specific sequence, carefully calculated by computer models to ensure the structure maintained its designed shape and strength. The deck installation used traveling cranes that could lift and position sections weighing up to 150 tons. These weren't your typical construction cranes. They were purpose-built machines riding on the bridge structure itself, with sophisticated computer controls to ensure each segment was placed with absolute precision. The tolerances were incredibly tight, often measured in single-digit millimeters. One of the most impressive aspects was dealing with the Adriatic winds, which can be fierce. They installed wind monitoring stations and had to carefully plan construction activities around weather windows. Some of the lifting operations could only be performed when wind speeds dropped below certain thresholds, requiring patience and precise scheduling. The project took 4 years to complete, opening in July 2022, and it stands as a testament to what modern construction techniques can achieve. It's bridges like this that remind us we're living in an era of engineering achievement that equals, and in many ways surpasses, the great building age of America's past. The Pelješac Bridge isn't just connecting land masses, it's connecting the ingenuity of the past with the technology of today, creating something that will serve generations to come. Now here's a story that'll remind you of the Great American Railroad expansion. Except this one happened in just 1 week. That's right, 1 week to install a complete bridge over an active railway line. The Osborstown project, near Sallins, Ireland, for Kildare County Council, is the kind of precision operation that shows just how far construction technology has come since the days when our great-grandfathers were laying track across America. NTHE Main Cork to Dublin Railway Line is one of Ireland's busiest rail corridors, carrying both passenger and freight traffic daily. You can't just shut it down for months to build a bridge the old-fashioned way. This project required what engineers call an accelerated bridge construction method, or ABC for short. This technique has become increasingly popular since the 1990s, and it's revolutionizing how we build infrastructure in tight timeframes with minimal disruption. NTHE's secret to their success was prefabrication. Long before that 1-week installation period, teams were working off-site to create every component of the bridge. Think of it like building a ship in a bottle, except you're building all the pieces separately and then assembling them with watchmaker precision. The bridge components were manufactured in controlled factory conditions, which meant better quality control and faster construction when it came time for installation. NTHE foundation work began months earlier, during scheduled railway maintenance windows. They used what's called a piled foundation system, with large diameter bored piles. Specialized rotary drilling rigs, mounted on tracked carriers for stability, would bore holes up to 1.2 meters in diameter and up to 20 meters deep. These machines use weighted Kelly bars and carbide-tipped cutting tools to chew through soil and rock. As they drill, they pump in bentonite slurry, a special clay mixture that prevents the hole walls from collapsing before the concrete goes in. And once the holes were prepared, they installed steel reinforcement cages, some weighing several tons, and then filled them with high-strength concrete using Tremy pipes. This method ensures the concrete flows from the bottom up, pushing out any water or slurry and creating a solid, defect-free pile. Each pile was tested using what's called a sonic echo test, where they measure how sound waves travel through the concrete to verify its integrity. NTHE Bridge Superstructure was a precast concrete design assembled from sections that were fabricated off-site to exacting specifications. These sections, including massive beam elements and deck panels, were transported to the site on specialized low-loader trailers. Here's where the planning really shines. Every delivery had to be timed perfectly, every route planned to the minute, because once that installation weekend began, there was no room for error. But here's the really clever part. They used what's called a self-propelled modular transporter, or SPMT for short. The entire unit can move in any direction, rotate in place, and even adjust its height hydraulically. For this project, they used SPMTs to move the precast bridge sections into position with millimeter accuracy, even in tight spaces where traditional cranes would struggle. NTHE railway possession, as they call it in the industry, began on a Friday evening. This is when the railway company hands over control of the track to the construction team. From that moment, it's a carefully choreographed dance of machinery and manpower. First, they removed the existing temporary works and cleared the railway corridor. Then, using the SPMTs, they maneuvered the first bridge beam into position. The crane lifted it onto the prepared foundation supports, where surveyors using laser-guided total stations verified positioning to within 2 millimeters. Then throughout the weekend, this process repeated for each major component. The deck sections were placed using a combination of crane lifts and hydraulic jacking systems. These jacks, positioned at strategic points, could make micro-adjustments to ensure perfect alignment. The joints between sections were filled with high early-strength concrete that could reach full strength within 48 hours instead of the usual 28 days. This special concrete mix includes accelerating admixtures and uses smaller aggregate sizes for faster hydration. One of the most critical aspects was maintaining the precise track geometry. Railways require incredibly tight tolerances. Even a millimeter out of alignment at high speeds can cause problems. They use sophisticated surveying equipment, including GPS-guided total stations that could verify positions to sub-millimeter accuracy, ensuring the new bridge wouldn't affect the railway's operation. NBY Monday morning, trains were rolling across the new bridge right on schedule. The whole operation was a masterclass in planning, precision, and the smart use of modern construction technology. It's the kind of project that proves sometimes the best way to build something is to build it somewhere else first, then put all the pieces together when and where you need them. That's the beauty of modern engineering, combining old-fashioned craftsmanship with cutting-edge technology to achieve what would have seemed impossible just a generation ago. You know, back in the day when the Brooklyn Bridge was being built in the 1870s, they were pushing the boundaries with steel cable technology. Everyone thought they were crazy. Today, we're witnessing another revolution in bridge building materials, and it's just as exciting. Let me tell you about something called the Bridge, the world's longest single-span bridge made from FRP composite materials, built by Mostastel Warzawa. Now, if you're thinking, what in the world is FRP? Stick with me because this is fascinating stuff that's changing how we think about building things. NFRP stands for fiber-reinforced polymer, and it's a material that combines the strength of fiber, usually glass or carbon, with the versatility of plastic polymers. Think of it like the fiberglass boats that became popular in the 1950s, but engineered to a whole different level. The concept isn't new. We've been using composite materials since World War II in aircraft construction, but using it for bridge building on this scale? That's pushing into new territory, and it reminds me of when we first started trusting aluminum in airplane construction. Now, let's dive into how they actually built this remarkable structure. The manufacturing process for FRP bridge components is quite different from traditional construction. Mostastel Warzawa used what's called the pultrusion method for many components. Imagine pulling continuous fibers through a heated die filled with liquid resin, kind of like making a really sophisticated piece of pasta, except what comes out is incredibly strong structural material with a precise cross-sectional shape. NFOR larger, more complex sections. They employed a technique called vacuum-assisted resin transfer molding, or VARTM. Here's how it works. They lay up dry fiber mats in a precisely crafted mold, seal it with a vacuum bag, then use vacuum pressure to draw liquid resin through the fibers. The vacuum ensures complete saturation and eliminates air pockets that could create weak spots. NTHE bridge deck panels were manufactured in climate-controlled facilities, which is crucial for composite work. Temperature and humidity can significantly affect how resins cure, so maintaining consistent conditions ensures uniform quality. Each panel was essentially a sandwich structure, FRP skins on top and bottom, with a foam or honeycomb core in between. This design provides excellent stiffness while keeping weight minimal, using the same principle that makes corrugated cardboard surprisingly strong for its weight. One of the most interesting aspects of working with composites is the bonding technology. Unlike steel bridges where you weld or bolt components together, FRP structures are often joined using high-performance adhesives. These aren't your hardware store glues. We're talking about engineered structural adhesives, often epoxy-based, that can create bonds stronger than the materials they're joining. The bonding surfaces are carefully prepared, often with abrasive blasting and solvent cleaning. Then the adhesive is applied under controlled conditions with precise thickness control. NFOR this project, they also use mechanical fasteners in critical locations, typically stainless steel or titanium bolts, inserted through precisely drilled holes. Drilling composites requires special tools. You can't just use a regular drill bit, or you'll delaminate the material. They use diamond-coated or carbide bits with specific geometries, operating at carefully controlled speeds and feed rates to create clean holes without damaging the surrounding material. NTHE main support girders were manufactured as multi-part assemblies. The production process involved laying up multiple layers of fiber fabric in precisely calculated orientations. This is called fiber architecture, and it's crucial for achieving desired strength characteristics. By orienting fibers in different directions through the thickness of the laminate, engineers can tailor the material properties to match the specific loads the component will experience. It's like creating a custom-designed material for each location in the bridge structure. And transportation to the construction site required special considerations. While FRP components are lighter than steel, they're also more flexible and can be damaged by improper handling. Specialized cradles and supports were designed to hold each component without creating stress concentrations. The components were transported on air ride trailers that minimize vibration and shock loads during transit. Inside assembly was where the lightweight nature of FRP really shined. Components that would have required massive cranes if built from steel could be lifted with much smaller equipment. They used mobile cranes in the 100 to 200-ton capacity range, which are much more maneuverable and easier to position than the giants needed for steel bridges. The crane operators worked with precision rigging, using soft slings that wouldn't damage the composite surfaces. An assembly required sophisticated alignment systems. They used laser guidance equipment to position components within 3mm tolerances. Temporary support structures, often made from steel scaffolding with adjustable screw jacks, held components in position during the bonding process. Here's something interesting. Because the adhesives used to join components need time to cure, the entire assembly process had to be planned around weather conditions. And temperature affects cure times, and moisture can interfere with bonding, so construction windows were carefully scheduled. The one unique challenge with composite bridges is connecting them to traditional concrete abutments and foundations. They developed special transition zones using hybrid assemblies that gradually change from composite materials to steel or concrete. These transitions use mechanical fasteners combined with adhesive bonding to distribute loads gradually, preventing stress concentrations that could cause premature failure. Quality control throughout construction was exhaustive. Non-destructive testing methods included ultrasonic scanning to detect any internal voids or delaminations, thermography to identify areas of improper cure, and visual inspection of every square inch of surface. Each adhesive joint was tested with pull-off tests on witness samples to verify bond strength. NTHE deck surface received a special coating system designed to provide traction for vehicles, while protecting the underlying composite from UV radiation and physical wear. These coatings, typically polyurethane or modified epoxy systems, were applied in multiple layers, with aggregate broadcast into the final coat for skid resistance. End load testing before opening the bridge was comprehensive. They positioned known weights across the span and measured deflections with precision surveying equipment. Strain gauges installed during construction provided real-time data on how loads distributed through the structure. The results validated the computer models used in design and confirmed the bridge performed exactly as predicted. This composite bridge represents more than just a new way to build. It's a glimpse into the future of infrastructure. It's innovation built on decades of materials science research, and it's exciting to see it come together in real-world applications. The techniques perfected on this project are already influencing bridge design worldwide, proving that sometimes the best way to honor the great builders of the past is to keep pushing forward with new ideas and better materials. There's something about building bridges across dramatic landscapes that captures the imagination, isn't there? Reminds me of the great railway viaducts our predecessors built through the American West. Today we're looking at the Urquez Viaduct in Tenerife, Canary Islands, built by Ferrovial, one of Spain's engineering giants. This isn't just a bridge, it's a statement about what modern engineering can achieve when confronted with challenging terrain. NTHE Urquez Viaduct crosses the Urquez Ravine at a height of over 150 meters, about the same as a 50-story building. Now, building at that elevation presents unique challenges, especially in the volcanic landscape of Tenerife, where the geology can be unpredictable and the winds are fierce. NTHE pier construction used a technique called jump forming, an evolution of the climbing formwork we discussed with the Pelješac bridge. Jump forms are self-contained units that climb the structure in larger increments, typically the height of one complete concrete pour. Each form section includes work platforms, safety rails, and hydraulic climbing mechanisms. After concrete is poured and reaches sufficient strength, hydraulic rams lift the entire form assembly to the next position. It's like the formwork is leapfrogging up the pier. These piers had to be extraordinarily strong to support the bridge deck at such heights, while withstanding wind loads that can be significant in exposed locations. The concrete mix design was crucial. They used high-performance concrete with additives that improved workability without compromising strength. Superplasticizers allowed them to place concrete with less water, resulting in higher strength and better durability. They also added silica fume, a byproduct of silicon production that fills microscopic voids in concrete, making it denser and more resistant to environmental attack. NTHE deck construction method for the Urquez Viaduct employed the balanced cantilever technique with sophisticated traveling formwork. The construction sequence began at each pier, with form travelers mounted on both sides. These massive steel structures, weighing around 200 tons each, roll along rails embedded in the completed bridge section. Each form traveler is a mobile factory, containing all the formwork, reinforcement assembly equipment, and concrete placement machinery needed to build one segment of bridge deck. Here's how it works. Workers assemble the steel reinforcement cage for the next segment within the form traveler. This reinforcement is incredibly complex, with dozens of different bar sizes and shapes, all interconnected. Pre-stressing ducts are also installed at this stage, plastic tubes through which steel cables will later be threaded and tensioned. Once the reinforcement is complete, the forms close around it, creating a precise mold. Concrete is then pumped up from ground level through a network of pipes and placed into the forms. The concrete placement has to be carefully controlled to avoid segregation and ensure uniform quality. And after the concrete reaches sufficient strength, typically 72 hours with high early strength mixes, the tensioning process begins. This is where post-tensioning technology really shines. Hydraulic jacks grip the ends of steel strands or cables, each capable of pulling with forces exceeding 500 tons. As the cables are tensioned, they compress the concrete, essentially preloading it to resist the tensile forces it will experience when carrying traffic. A computer controls the tensioning sequence, ensuring balanced forces that maintain the correct bridge geometry. Once tensioning is complete, the form travelers advance to the next position, and the cycle repeats. It's a methodical, precise process that can complete one segment every 4 to 5 days. As segments are added on both sides of each pier, the cantilevers grow toward each other until they meet at mid-span, where a closure pour completes the connection. An NTHE final bridge deck received a waterproofing membrane system to protect the underlying concrete from water infiltration. This membrane, typically a polymer-modified bitumen product, was applied using specialized equipment that heats and rolls the material onto the prepared deck surface. An asphalt concrete wearing surface goes over the membrane, providing a smooth, durable riding surface for vehicles. When completed, the Urquez Viaduct stands as one of the most impressive structures in the Canary Islands, a testament to Ferrovial's engineering expertise and the skill of the construction workers who brought it to life. It's bridges like this that remind us the golden age of engineering isn't behind us. It's happening right now, all around the world, as dedicated teams push the boundaries of what's possible. Every time someone drives across this viaduct, they're experiencing the culmination of centuries of bridge-building knowledge, applied with modern technology to create something that will serve generations to come.